Our focus today will be on setting up material balances, which are also called mole balances or mass balances. But before we dive into them, let's talk about why we need them. So imagine that you're trying to design a process where a reaction is happening. So here's your process. Maybe some things go in, some things go out, and it's part of a chemical plant. You have to decide, what components to add and at what concentration or flow rates. You also need to pick a container volume of some kind to use for this reaction. You'd also need to decide what temperature to run this reaction at. And you'll probably make these decisions based on some desired goal here for how much of a product you want to make. So product, this might be a product concentration or flow rate because you're going to want to make some product maybe over time. So product info, and we'll say desired product info. So these are things that you want to be thinking about in terms of why we're studying kinetics in the first place. And these are just some of the basic concepts. Eventually, later on in this course, you'll want to learn how to maximize, say, your desired product over undesired products. So increasing your desired product, decreasing undesired products. And also related to this question of temperature here, you'll want to, figure out how much heating or cooling to perform to keep this reaction under control at whatever temperature you decide is best. So for all these tasks, you need to set up and use mole balances. So mole balances help you solve or determine these parameters. And that's why we're going to spend a lot of time talking about them. And because everything in this course, most everything builds off of this, you'll really want to pay close attention to this material. So one quick note, I used to think material balance, mole balance, mass balance, all kind of interchangeable. A material balance is sort of referring to either of these, but there is a difference between a mass balance and a mole balance here. And the important difference that I want to get at is that there's conservation of mass and energy, as we know, and we'll get to that later in the course. But there is not, so versus no conservation, not necessarily conservation of moles. Conservation of moles. And we know that just thinking of, a particular example, let's say we just have a reaction where A goes to 2B. We know that at the end of the day, there has to be the same amount of mass on either side, but we're clearly seeing based on stoichiometry that there isn't going to be conservation of moles. If you start with 100 moles of A to begin with and your reaction goes to completion, you'll have 200 moles of B. And so that's really important as we think about kinetics, especially this study of fluids that might not be that are compressible, and how some of these changes in moles might be required for analyzing them. So where we're going is to basically then take these mole balances and get towards our ultimate goal of design equations, which is what we call essentially any of these simplified equations that govern what happens in a particular reactor system. So now if we want to start working our way towards a design equation, rather than focus on a particular type of reactor, we're going to start with a general mole balance. And so this way we can use it to come up with any of our design equations. And so here we're thinking about an arbitrary volume. This way we aren't too oriented around a particular kind of geometry. So the shape, shown here is deliberately meant not to be a circle or a box. I'm not just really bad at drawing circles or boxes. So here's our reactor volume. And now we're going to do a balance on this. Assumptions here. One is that the reaction is only happening inside here. So reaction only occurs here. This way, if we have streams of, say, product or just anything that comes out of this reactor, let me just draw something representing a flow out. There's no reaction happening at this point anymore. We're just kind of saying that it's confined to this system boundary here. Okay. So the other assumption, which is kind of represented here already, is that this control volume can take any shape. Now we're going to go ahead and draw something going in, and we're going to get into the weeds a little bit here about what kind of terms could be involved in this situation. And there aren't so many at a high level. If we're thinking about our terms, I'll just stick with blue for now. We're going to have species that come in. So we'll just refer to for species I. So maybe it would help actually just to think about our sort of overall balance equation in more familiar terms. We know that there are, let's see, accumulation equals in minus out plus generation minus consumption. Okay, so we're going to be thinking about all of these things. So if we think about the in case, we're going to have in a system in which things could be flowing, which is the most general sort of case, we'll have a molar flow rate of species I coming in. And in this course and probably in your past courses, you're going to see the subscript 0 or O or not. Fi not, don't confuse it with an O for out. It is just the initial molar flow rate in. And similarly, you can interconvert to an initial concentration of species I. And you can do that interconversion using volumetric flow rate, which is represented with this, kind of cursive V here, not to be confused. This little v with the extra flourishes for your capital V, which is what we use to describe the volume of the reactor. And sometimes I give that a subscript, capital R, just to help distinguish these two. Okay, so we've got a volumetric flow rate coming in. We've got, if we really just look at species I here, we've got molar flow rate, an initial concentration. Once it's in the reactor, this volume is likely different, than well, it wasn't in a volume before. So we may well have a different concentration here of species I. And what we're also going to have, which is new in this course, is something to deal with these generation and consumption terms. But I'll come back to that in a second, just sort of going in order here. So we have in, let me go ahead and do the out. So like I said, with the subscripts, what we use in this course, we sort of think about our molar flow rate of a species as just what it is coming out. So there is no separate prefix usually given for the final concentration or final molar flow rate. Okay, so that covered the what's going in, what's going out. Now we just need to think about generation and consumption. So in kinetics, we lump these two terms. We sort of lump them into a net generation. And that makes sense. You know, intuitively, a reactant is getting consumed, a product is getting generated. Maybe if a certain species is both a reactant and a product in different reactions, you can think of its change being some kind of net generation, and it could have a positive or a negative sign. We're going to represent that with this capital G sub I. And so we have this G sub I term here, which I'm gonna, you know, decorate just to draw attention to it. And that is, you know, the real new addition in this course. Now, something that I have sort of done here is I've assumed you know, that the generation term is the same throughout the reactor, and that the throughout this volume, and that the concentration of species I is the same throughout the reactor. So it is possible that within this reactor volume, we might not have something that's spatially uniform. And so we don't, if we want this general balance to be as generalizable as possible, we don't want to assume that there's just one concentration and just one generation term throughout the entire reactor. So we'll keep that in mind. If you look, for example, at a similar figure in your textbook, I think it'll refer to you know, maybe CI1 and CI2, just to note that, you know, the concentration of species I could vary. So that is our overall balance, just kind of shown pictorially. If we want to be able to write this out now, we go back. I'll just simplify here. And we know we've already made this actually some kind of just net generation. Okay, so now if we want to take these terms and think about what's actually happening in that volume. Okay, so we have a volume, and if we're thinking about the accumulation term for a given species, we have a certain number of moles that are in that volume, and accumulation is how much of that amount of moles is changing over time, right? We know that, so it's a time derivative. If we think about what was going in, that was our F of I. And let's just do a quick check here to look at units. So I'm gonna try not to use too many colors here, but okay. So let's just see units in this case. We have moles per time, okay, and this is a molar flow rate. So we have moles per time here. So these check out. Actually, just to avoid confusion here, let me do that. Okay. All right, so we have, sorry, what was coming in, maybe you would have caught this already, is actually Fi naught, right? And then it's Fi that comes out. And so then we just have to deal with this generation term. And in fact, that's exactly why we have this net generation Gi, and we know then that the units of this must also be moles per time. And we're also going to define, you know, G sub I here as the net generation is basically occurring in a given volume, and we want to integrate that across the whole volume. So we're going to represent it here as a triple integral across, whatever three coordinates or dimensions might represent volume of r sub I dv. And you'll remember from the previous material that our r sub I here is the rate of formation of species I. So this is where we've made the connection now. This GI term is unifying. Unifying our material balance, and the actual kinetics rate information. And so this is then why we care so much about being able to properly define this kind of rate of formation of species I term, because that's going to come in and affect our material balance.